there. My name is Ian Asasa. Today I'm going to be taking you through quantum mechanics. In specific, we shall be covering the practical sessions. So today we're going to be looking at the quantum random number generator, QRNG, which is a practical application of making purely random numbers in quantum computing. So we shall start with the classical overview. And in classical computing, we have pseudo-random number generators. So, what are pseudo-random number generators? As you can see here, in classical computing, we use pseudo-random number generators, and these rely on mathematical formulas. And if the initial seed is known, then they may become irrelevant. This can be used in cryptography, modeling, and simulation. So, this randomness looks random in classical computing, but since it has mathematical equations, and if a seed is known, then it can be determined. However, in quantum computing, it is different. How do we do this? We rely heavily on principles in quantum mechanics to achieve this. So, how shall we do this? I'll give you a simple analogy. In classical computing, or in the classical world, when you have a coin and you flip it, you get two sides, either the heads or tails. So, we always assume that it's random, and it is because of the ignorance of certain factors that contribute to this output at the end. For example, force, air resistance. If you know these things and all these things that contribute to this coin, then you can know whether it's heads or tails. In quantum computing, it's different. We do not know the output. The reason is because of Bell, the experiments that were carried out by John Bell in the 1960s to date, and they realized that when they carried out certain experiments on photons and atoms, there were no local variables that contributed to the output of them, which made quantum mechanics purely undeterministic, and we are going to look into there. So there are three steps we do to make a purely random number. First of all, we start with the state of the qubit. Say at state 0, get state 0, we apply the Hadamard gate, and then we measure in computational state. So I'm going to explain these three steps and how they occur. So we start with a qubit at get state 0. We apply the Hadamard gate. The Hadamard gate, remember, gives us an equal superposition of the qubit. What does this mean? It puts it in a 50% chance of a 50% chance. So we have a 50% chance that it will be 1 or 0. This is a quantum state, and its state is highly undeterministic. So when we measure it in computational state, that means we want the answer in 1 or 0. We get a probability distribution. This probability distribution is represented by Schrodinger's equation, which is this one. You can go in detail for more of it. It simply tells us the evolution or how the quantum state for the particular qubit is behaving, but it does not tell us the output. So, when we measure the computational state, the wave function collapses. The wave function is not physical. However, it's a bunch of amplitudes. And so when it collapses, as we said in quantum mechanics, it's undeterministic. When it collapses, we get an answer. Okay, so in this example, we're going to use the AER simulator by Qiskit from IBM to do this. We are going to use a 2-qubit system, and we're going to create 4 equal superpositions, each having a quarter percent chance. How are we going to represent this? We shall have each, for example, the first qubit 00, 01, 10, 11. Now this is in binary. This represents 0, 1, 2, and 3. Okay, so to do this, the Jupyter Notebook, we're going to explain this. And when you look at this Jupyter Notebook, you'll see that number of bits is 2. That means we're dealing with a 2-qubit system. And then you can see down there that we create the quantum circuit by passing in these arguments, the two bits. Then we shall make a for loop, and the for loop is going to apply the Hadamard gate to each position of the qubit. Then we measure the state. So in the end of this code, we shall have an output, and you can see that it demonstrated that it generated a binary string 1, 1. This represents 3. Okay, and this shows us that it's purely random. However, you should note that the simulator AER does not actually give us real quantum possibilities. And this is because it is a simulator running on a classical machine, so it relies heavily on pseudo-random number generators. If you want to test this in real life, you go to IBM, get the API, and try it out. So this is most of what we have to cover today. But if you want to explore much more, I believe this can be very handy in areas like cryptography to improve the cryptographic system, because these numbers are purely random. As the future goes on, the computers will be able to factor large numbers and break certain encryptions. And so this could be an interesting area to study. Thank you so much. Right, as promised, you have to cover the lab. Okay, so this is the notebook that implements quantum random number generator. So we import Qiskit. Qiskit is the IBM library. I'm going to make this short but precise. So from Qiskit we import quantum circuit. This enables us to draw quantum circuits. From Qiskit AER we import the AER simulator. This enables us to run a quantum simulator on a classical machine. So it doesn't really do the exact classical output, but it does mimic it. So it lacks the ability to maintain the quantum physics, but it's just a simulator. The number of bits are 2 and shots are 1. This means that we're going to execute once or measure once. Yeah. We create a 2-qubit circuit, and it's going to be with 8 classical bits for measurement, and that means that we can draw up to 255 integer. Okay, so we apply a Hadamard gate to this circuit using the for loop. So we shall apply a Hadamard gate to the circuit. Remember, Hadamard gate creates a
an equal superposition, which is an entangled state. So we need a quantum state to actually get quantum randomness, to get random numbers. We need to be in a quantum state, and that's Adam and Gate. We measure the output, okay, and this line of code is for printing, which is going to tell us that the circuit is here. Yeah, so we store this AR simulator function in this variable, then we pass it into the transpile function along with a quantum circuit. We run a job according to the number of shots along with this function that has the simulator and the quantum circuit to be run. We store the results from this job, the result function variable. Then we get a measurement from this, and then we get a random number, a random binary number, and then we convert this back to decimal. When you run this, you can see that we generated a binary string 10, which is equivalent to 2. Yeah, that's much of it. Thank you, and you can also implement this by installing Qiskit runtime on your machine, and you can run this as well. Right.